Welcome to the ultimate grade 9 learning experience. Every chapter becomes simple when it is visual, interactive, and exciting. Watch and understand every textbook concept with complete confidence. Visit rehanstudio.com for new CITES practice questions, revision support, and exam success. Students, let's see how Newton's second law helps protect people during road accidents. When a moving vehicle's sudden body continues moving forward because of inertia, the airbag increases the time for the stopping time, means a smaller acceleration and therefore a smaller force. This reduction seat pads are real-life applications of Newton's second law and save millions of lives around the world.
Example 6.5, Part 2. Now push with 55 newtons. Friction takes 50 newtons, leaving a net 5 newtons. Then acceleration equals force over mass, that is 5 over 25, giving 0.2 meters per second squared. And in 2 seconds, it moves s equals 1/2 at squared, giving 0.4 meters forward. See how we chained the formulas together neatly? Example 6.6 setup. Here's a graph reading problem. A 1,500 kilogram car with a velocity time graph in 3 stages. We'll find the force in each stage. The trick is, the slope of the graph gives us acceleration. Example 6.6, Part 1. In the first 5 seconds, the car speeds up. So acceleration is 2 meters per second squared. Then F equals ma, that is 1,500 times 2, giving 3,000 newtons toward the east. A real net force is pushing it forward. Example 6.6, Part 2. In the middle stretch, the graph is flat. Constant velocity, no change. By the first law, that means zero net force. The engine's push just balances friction here. Example 6.6, Part 3. In the last stage, the car slows down, so acceleration is negative, minus 2 meters per second squared. The force comes out as minus 3,000 newtons. The minus sign simply means it points backward, toward the west, braking the car. Signs tell direction. Pause and ponder. Toy car. A toy car rolls at a constant velocity. What's the net force on it? Don't be fooled by the mass. Constant velocity means no acceleration, so the net force is exactly 0. Pause and ponder. Swings. 2 children of different weights on swings. To give both the same acceleration, which one needs a bigger push? The heavier child, of course, because F equals ma. More mass demands more force. Pause and ponder. Bubble wrap. Why do we pack glass in bubble wrap or hay? Think of the cricket catch idea. The soft padding stretches out the stopping time during a jolt, reducing the force. Less force, no breakage. Physics in your parcel. 2 objects interact. A force is never a lonely thing. It always needs 2 objects. Kick a football and notice your foot feels the ball pushing back. So whenever you push something, something pushes you. Let's explore this fascinating idea. Push the table. Sit on a wheeled chair, lift your feet, and push a heavy table away from you. What happens? You roll backward. You pushed the table forward, but the table pushed you back. Try it. It's great fun. Pull the table. Now pull the table toward you instead. This time your chair rolls forward toward the table. Whichever way you act on the table, it reacts on you the opposite way. Do you see the pattern forming? Conclusion. Every single time the table pushed or pulled you back just as hard in the opposite direction. That's our big clue. Forces always come in pairs, acting oppositely. Bicycle without pedaling. Sitting on a cycle without pedaling, push the ground backward with your feet, and you glide forward. You pushed the earth back, the earth pushed you forward. That's the third law carrying you along. Walking and running. In fact, this is how you walk and run every day. Your foot pushes the ground backward, and the ground pushes you forward. You never noticed, but the earth has been pushing you your whole life. Friction helps you move. And guess what supplies that forward push? Friction. So here friction is your friend, helping you move rather than stopping you. Without it, your feet would just slip. Bridging. Grooves and treads. That's exactly why shoes have grooves and tires have treads, to boost friction and grip. And it explains why wet floors or icy roads are dangerous. Too little friction, and your feet or tires slip. Everyday safety, all from the third law. Forces are equal. Now, are the two paired forces exactly equal, or is one bigger? Experiments settle it. They are equal in size always. Let's prove it with a simple setup. Connect spring balances. Hook two spring balances together and fix one end to something firm. 2 force meters, face to face, perfect for checking our claim. Predict and observe. Before pulling, predict. Will the two readings match? Now pull the free end and check. Every time, same reading on both. Try different pulls, they always agree. What it shows. Equal readings mean the two balances pull on each other with equal force, in opposite directions. Your prediction, I hope, came true. This is solid proof of the third law. Statement of third law. Here's the law in full. Whenever one object pushes a second, the second pushes back at the same instant equally hard in the opposite direction. To every action, there's an equal and opposite reaction. Note, pairs on different objects. But mind this crucial point. The two forces act on different objects, never the same one. That's why they don't cancel each other out. Never mix this up. It's the most common mistake students make. Climbing a coconut tree. Watch someone climb a coconut tree. Their legs press down on the trunk, and friction pushes them up by an equal force. That's why a smooth, slippery trunk is so hard to climb. Less friction, less upward push. Rowing a canoe. Remember our opening canoe question? Now you can answer it. The paddle pushes water backward, and the water pushes the paddle, and the whole canoe forward. The two forces act on different things, so they don't cancel, and off you go. Threads. What else affects canoe speed? Of course, real rowing isn't only about the push. Water drag, currents, the boat's mass, and even rowing style all affect how fast the canoe goes. Physics gives the main idea, the real world adds the details. Rockets and the third law. Now for something thrilling. Rockets. A mighty rocket blasting into space obeys the very same third law as our humble canoe. Let's understand it with a fun balloon experiment first. Balloon rocket setup. Blow up a balloon, tape a straw to it, and thread it onto a tight string tied between two nails. Congratulations, you've just built a balloon rocket. Release and observe. Let go of the neck and whoosh, the balloon zooms along the string. The air rushes out one way, and the balloon shoots the other way. Simple and utterly delightful. Why the balloon moves. Why did it move? The stretched balloon pushes the air out backward, and by the third law, the escaping air pushes the balloon forward. Action and reaction, right in your hands. How a rocket works. A rocket is just a giant, powerful balloon. Its engine flings hot gas downward, and the gas pushes the rocket upward. When that upward push beats the rocket's weight, it lifts majestically off the ground, slowing in space. And to slow down in space, a rocket fires its engine in the same direction it's moving, so the gases push it backward. Our own Chandrayaan-3's Vikram lander did exactly this to gently touch down near the moon's south pole. Proud moment, and pure Newton. Note, pairs don't balance. One more time because it's so important. Action-reaction pairs act on two objects and never cancel. But two equal opposite forces on the same object do balance. Always ask, which object? That's the key. Pause and ponder. Fire hose. Why does a firefighter grip that hose so tightly? The hose throws water forward with great force, so the water pushes the hose backward just as hard. That backward kick is what they're wrestling with. Pause and ponder. Spacecraft. Out in deep space with almost no gravity, how does a spacecraft turn or speed up? By throwing gas out one way and getting pushed the other way. The third law is the only way to move where there's nothing to push against but your own fuel. Contact and non-contact forces. Does the third law work only when things touch? No! It works for all everyday forces, whether they touch, that is contact, or act from a distance, that is non-contact, like magnetism and gravity. Non-contact examples. Two magnets, two charged balloons, or the earth and a falling fruit. None of these need to touch, yet each pair pushes or pulls the other equally and oppositely. Distance doesn't break the rule. Example 6.7. Earth and fruit. A puzzler. If the fruit and the earth pull each other equally, why does only the fruit fall? Because of F equals ma. The Earth's mass is so enormous that the same force gives it an acceleration too tiny to ever notice. The fruit, being light, races down. Example 6.8. Bullet and gun. When a gun fires, it pushes the bullet with 2 newtons, and the bullet kicks the gun back with 2 newtons, equal forces. Yet the light bullet gets 20 meters per second squared, while the heavy gun only gets 0.4 meters per second squared. Equal forces, very unequal accelerations, thanks to their different masses. Note, equal force, unequal acceleration. So carve this into memory. Equal forces do not mean equal accelerations. The lighter object always accelerates more. Force is shared equally. Acceleration is not. Can laws handle connected objects? So far, we studied single objects. But what if 2 objects are tied together and pulled? Can Newton's laws still help? Absolutely. And there's a clever shortcut. Let's see. 2-box setup. Picture 2 boxes on a smooth, frictionless floor, joined by a string. You pull the first box with a force F, and the string drags the second box along. A little train of 2 boxes. Tension force. The string pulls both boxes. This pull is called tension, T. And by the third law, the 2 boxes pull on each other through that string equally and oppositely. Forces on each box. Let's list the forces. Box 1 feels your pull F to the right and tension T to the left. Box 2 feels only tension T pulling it right. Draw these arrows. They make everything clear. Approach 1. Separately. One way to solve it is the long way. Study each box on its own, find its net force, and apply F equals ma to each. It works, but it's a bit of effort. Approach 2. Single system. Here's the smart shortcut. Treat both boxes and the string as one single system. Then we only worry about forces from outside and ignore the internal tug between them. Much simpler. Internal versus external. The tension T is inside our system, so it cancels out and we can forget it. Only your pull F comes from outside, so only F matters. Choosing the whole system as one saves us all the fuss. System acceleration. So the 2 boxes accelerate together as A equals F over the sum of m1 and m2, exactly as if they were one big box of combined mass. Neat, isn't it? The whole moves as one. Vertical forces balance. What about up and down? Gravity pulls the whole system down, and the floor pushes it up with an equal normal force. They balance, so there's no vertical motion. Only the horizontal pull matters for acceleration. Threads, the power of whole. This idea is powerful beyond boxes. Even though your arms and legs swing in complicated ways while walking, we can treat your whole body as a single object. Science often becomes simple the moment we look at the whole instead of the parts. Friction summary. Let's gather our treasures. First, friction always acts opposite to the direction of motion, the ever-present force that slows moving things down. First law summary. Second treasure. The first law. Things keep doing what they're doing, resting or moving steadily, until a net force disturbs them. The law of laziness, or inertia. Second law summary. Third treasure. The second law. F equals ma. A net force accelerates an object in its direction. More force giving more acceleration, and more mass giving less. Our workhorse formula. Third law summary. Fourth treasure. The third law. Every action has an equal and opposite reaction, acting on a different object. 3 laws, and you can explain the moving world. Well done.
Students, when several forces act on an object, we combine them to find the net force. We simply add their magnitudes. When forces act in opposite directions, we subtract the smaller force from this object is called the net force. Net combined FF alter an object acting on its directions. To understand motion, we must always identify the net force acting on an object. Students, let's see how Newton's second fiend helps protect people during road accidents. When a moving vehicle's sudden body continues moving forward because of inertia, the airbag increases the time for the stopping time, means a smaller acceleration and therefore a smaller force. This reduction seat pads are real-life applications of Newton's second law and save millions of lives around the world. Students, let's quickly review everything we have learned about force is a push-pull that can start motion, change speed, change direction, even change shape. We learned its force piston, this motion law. Physics helps us understand the world around us. Keep questioning, keep exploring, and keep learning. Congratulations, students. You have successfully completed Chapter 6, How Forces Affect Motion. Today, we learned how forces influence every movement around us, from everyday actions to powerful scientific discoveries. Keep observing, keep questioning, and keep exploring the facts. Until next time, and stay curious and keep learning. Goodbye, students.
Class 9 and 10 students. Don't worry, make science and social science easy with your CBSE teacher. Subscribe now, like, comment, and press the bell.